First derivative test. The first derivative test gives us a way to determine if a critical number is in fact a maximum or a minimum value of a function instead of an asymptote or an inflection point. The idea is to determine if the function is increasing and decreasing on either side of the critical number, or decreasing and then increasing. So critical numbers are values of a function where the tangent line is either horizontal or vertical, also known as a turning point. The test for a first derivative says that given c, which is a critical number for a continuous function of f, if the derivative of f of x changes from positive to negative at c, then that is a local maximum. So let's look at that on the graph. So if we are going from a positive, so here's a positive slope, to a negative slope, then this is a local maximum. And if the derivative of f of x changes from negative to positive, so it goes from negative to positive, then we're going to get a local minimum. And if the derivative of f of x does not change sign at c, so that would be right here, then it isn't a maximum or a minimum. So this is going down, and then it is still going down. So this would have, the derivative would equal 0 here, but it's not a maximum or a minimum. So let's try an example. Step 1 will be to find the critical numbers, and I'm going to do that by taking the derivative and seeing when the derivative equals 0. So I'm going to factor out this 3, and then I'm going to see for which values of x this can equal 0. So I have found that this will equal 0 when x is 2 and when x is negative 2. So there's a couple different ways we can go next. So let's try plugging this value into the derivative of the function. So let's say if f of x, when x is less than negative 2. So like let's say negative 3, for example. So if x is negative 3, then that would give me 9 times 3 is 27 minus 12. That would give me a positive value. Let's say if x is less than negative 2, greater than negative 2, but less than positive 2. Like, let's say it's 0, if this is 0. Well, that's going to give me 3 times 0 is 0. That's going to give me a negative output. And let's say if x is greater than 2. So let's use 3 again, and that would also give me a positive output. Let's draw the graph of this function, the derivative. Okay, so this is a parabola with an intercept at negative 12. And at negative 2 and 2, it goes through the x-axis. Okay, so when x is less than negative 2, I am in the positive region. That's right here. When x is in between negative 2 and 2, I am in the negative region. And when x is greater than positive 2, I'm in the positive region. So the derivative, as you go from less than negative 2 to greater than negative 2, goes from positive to negative. This indicates that f at 2, not the derivative, is a max. As you go from 2 to greater than 2, you're going from a negative to a positive. Oops, sorry, that should be a negative. So f at positive 2 is a minimum. Let's try another example. Okay, step 1, I'm going to take the derivative to find the critical numbers. So I'm going to have 4 over 2, which is 2x cubed minus 14x squared plus 20x. Now I'm going to factor to make my life easier. Set it equal to 0 to find where my critical numbers are. Okay, so I've got 3 critical numbers here. If x is 0, this is true. If x is 5, this is true. And if x is 2, this is true. Okay, and this time let's start with the graph. So I know I have a critical number, a 0 value at, this is the graph of g, the derivative of g of x, at 2, or I mean at 0, at 2, and at 5. Okay, I can also just remember that because I have a cubic function here and my leading term is positive, that this graph is going to start in this quadrant. I know that I'm going to go through each of these points. I don't know where they're going to turn around, but I know that they're going to pass through each of those points. Okay, so in this one, I'm going from a minimum to a maximum. So from a negative to a positive, so this is a minimum. This one I'm going from a positive to a negative, so this is a maximum. And this one is going from a negative to a positive, so this is also a minimum. I can also plug some values into g of x to see what this looks like as well. So, or the derivative g of x. So if g of x is less than 0, so I put in to here a value less than 0, I'm going to get a negative outcome. If g of x is in between 0 and 2, so let's say I put 1 in there, then I'm going to get a positive outcome. And if g of x is in between 2 and 5, I will get a negative outcome. And if the derivative of g of x is greater in a value domain greater than 5, then I will get a positive outcome. And so these regions correspond to these areas on the graph. Okay, for homework, try page 182, numbers 1, 2, and 5. And as a reminder, you can also make that table where you test out the different regions, these different regions. They can go as columns on this table, and you can put like 2 of x, x minus 5, and x minus 2 along this way as well to figure this out too. That's another strategy as well.